Welcome to Kinematics Lesson 1, and I'm making this video to show you the process that I use to solve kinematic equations. From my experience, if you don't have a problem-solving strategy or process, you're probably not going to get very far in physics. So I'm going to show you the process that I use, and hopefully after you see me do it a couple times, you'll be able to do it yourself. So to demonstrate that this process works, I'm going to use it on just some run-of-the-mill kinematic problems that I found online. And I haven't worked these in advance, so hopefully this experiment works. So this is the physicsclassroom.com, and these are just some random kinematics problems. So I'm going to add it to my PowerPoint slide. Just copy and paste it. Now I got the problem. And so let's see if we can solve it. So I copy pasted the problem into the PowerPoint. I got my kinematic equations over here to the right. And let's read the problem. An airplane accelerates down a runway at 3.2 meters per second. That's an important piece of information. For 32.8 seconds until it finally lifts off the ground. Determine the distance traveled before takeoff. So those are the three clues I get right off the bat from reading the problem. So I can go ahead and write those down in my givens. And that's 3.2 meters per second squared. And that is an acceleration. The units, meters per second squared, always indicates acceleration. And the time, 32.8 seconds. So we know if we see seconds, that equals time. Okay, and then it's asking me to determine the distance traveled before takeoff. So if it's asking you to determine the distance traveled, then it's asking you to determine delta x. And that is your unknown. So here we have three variables, a, t, and delta x. But if I look at these equations, let's see, delta x, xi, vt, we don't have v. V we don't have, v we don't have, and v we don't have. So none of these equations we can use because we don't have v, and v is not our unknown. So maybe we need to look at this problem a little more closely. And I'll start by drawing a picture. Drawing a picture sometimes helps physics problems. So here we have an airplane taking off. It starts here, and the airplane starts from rest. So every airplane must start from rest because that's when all the passengers get on and they load all the luggage onto the plane. So its initial velocity before it takes off is 0 meters per second. And what else can I say? From this picture, I can say that that's x initial and that's x final. And the distance between them is delta x. And so I can say that delta x is equal to x final because x initial is 0. In other words, we're starting is 0, and then we're counting how many meters it takes for the plane to travel before it lifts off. So now we can put these two pieces of information into our givens. And so now we have 5 variables. We have 1, 2, 3, 4, and 5. Okay, so we got 5 variables. This equation has 1, 2, 3, 1, 2, 3, 1, 2, 3, 4, 5. So this t is in there twice. 1, 2, 3, 4. So this one has 5. So let's use that one. So that equation says that delta x equals x initial plus velocity initial times time, so 1/2 at squared. Okay, so now we can just plug in our numbers. X initial equals 0 plus vi initial. Vi equals 0. T is 32.8 seconds. Fix that 8. And then plus 1/2 a. What's a? 3.2 meters per second squared times t squared, which is 32.8 seconds, and then that's squared. Okay, so we can simplify that even more because this is 0. So if it's 0, it doesn't add anything to the equation. So let's take that out, and then this is 0 times 32.8. So anything times 0 equals 0. So you can get rid of that too, because those are both 0. And we have 1/2 3.2 meters per second squared times 32.8 seconds. Then square that. So I'm going to work that out on my calculator to get my solution. So I'm going to use the calculator on my phone. Okay, so 0.5 times 3.2 times 32.8 times 32.8, because it's squared. So let's see. 1/2. Oops, did that wrong. All right, one more time. So 1/2 times 3.2 times 32.8 times 32.8. And I'm getting 1,721. So that is my answer, 1,721. What units is that? Well, it's delta x, so it's going to be meters. And so let's check and see if I got that right. So the answer, 1,720. Close enough. Sometimes I'm sure they rounded it up or down depending on significant figures. But correct answer, D equals 1,720 meters. We use delta x, they use D. Doesn't make any difference. Alright, so that wraps up the first example, and I'll work some more for you in the future.